Right, so today's topic is about how to use L'Hopital's law to find the limit. We're going to talk about L'Hopital's law. So why we have to study that? Well, we find out be much easier if we apply L'Hopital's rule in a correct way and can quickly find the limit. Now, for some function which is written in the form a quotient of one function over another function. Okay, so we're going to study the limit as x approaches number a. Okay, and here we have two functions in general. Well, if both are functions continuous and g of a is not going to be 0, you just needed to plug a for x. Then you get the limit. Now, but that's not the usual case. In many cases, the limit of g of x is going to be 0 or infinity. Okay, so in that case, we can use a L'Hopital's law to find the limit. Okay, so here's some situation. If the limit as x approaches a, f of x equals the limit of g of x both equal to 0. That's called the 0 over 0 type. Right? Or the second case, if this is going to be plus minus infinity, and this will be plus minus infinity. So that's called the infinity of infinity type. And then you can find the limit using their derivative. As long as if the limit of the derivative exists, then that should be equal. So you can, if the limit on the right side exists, right? If the limit on the right side exists, okay? Now sometimes you have to continue. If it's still 0 over 0 type of infinity over infinity type, then you can differentiate again and again. The numerator differentiate the numerator and denominator. Then you look at the next quotient. Okay. So here's some examples. But we have to be very careful. We have to check the conditions when we apply the L'Hopital's rule. Otherwise, you will make mistakes. All right. So look at that. When x approaches what? All right. When x approaches what? Then denominate. Yeah, this is a natural log of 1 is 0. Remember that, right? So then it's going to be 0 over 0 type. Right? When x approaches what? The numerator approaches 0. The denominator approaches 0. Then you can apply the L'Hopital's rule and differentiate the numerator and differentiate the denominator. Okay, and you were surprised that this is going to be a very simple function. The denominator is 1, the numerator is 1 of x, and clearly this simplified function is going to be just 1 of x. And then when x approaches 1, that's just 1 of 1, it's 1. Okay. Okay. Why is the L'Hopital's rule is true? Now let me, it's wonderful. It's a powerful formula, right? So the idea is, the proof of, this is the proof of L'Hopital's rule. Okay. We take a look at the limit, right, of f prime x, g prime x. Okay, we assume that we just assume that in the case f a equals g of a equals 0. I just explained to you. Okay, this is the case. Give idea of why it's true. Otherwise, how can I trust you? This is always right. So this is going to be just look at this special example. Okay. Okay. So this is going to be the limit, assuming g prime is not going to be 0. I just look at this case. Okay. G prime. So you just stop there, find the one derivative, find the derivative of the function, then you find out the denominator is not going to be 0 when x equals 8. Then just find the limit, right? In this special case, it's easy to understand. So but how do you find the derivative? The derivative is going to be calculated in the following way. It's going to be x minus a, right? Here's g of x minus g of a. Okay. All right. Then this is a limit. The quotient of limits is going to be the limit of that quotient. So you can here's g of x minus g of a divided by x minus a. So you simplify this quotient, x minus a will be gone. So you have fx minus f of a, g of x minus g of a. Okay? And then again, since we already assumed that f of a, g of a is going to be 0, this is 0, right? This is 0. So you can simply get this. Okay? Then look at that, right? So the limit of the derivative, the quotient of the derivative is going to be the limit of the original function. That's the idea why it's guaranteed. Otherwise, after you differentiate the numerator and denominator, how can you get the same limit, right? So this is I just give you a simple argument in this case, okay? And in this case. Okay, so let's take a look at the next problem. The limit as x approaches pi, right? And that is going to be sine x over sine x. All right, so first of all, this is 0 over 0 type. Because when x equals pi, sine pi is 0. So it's 0 over 0 type. Sine pi equals 0. So you can apply the L'Hopital's rule to find the derivative. So it's going to be the derivative numerator is just 1. The derivative of the denominator is going to be cosine x. But the cosine pi is going to be -1. So it's going to be 1 over cosine pi, which is going to be -1. So the answer will be -1. Now let's try the next one. Okay. So the limit as x approaches the x approaches 2, x minus 2, x cubed minus 8. All right. So how do you find the limit of this? Now, if you use a L'Hopital's rule to find this limit, it'll be very simple. Okay. You just need to. This is 0 over 0 type because 2 cubed is going to be 8. So that's why it's 0 over 0 type when we plug 2. Okay. All right, so you can apply the L'Hopital's rule, and this is a derivative denominator is 1. The derivative of the numerator is going to be 3x squared. So now it's not going to be, you cannot use the L'Hopital's rule to this quotient because it's not a 0 over 0 type. You have to stop there. So you plug 2 for x, get 12, right? So that's the answer. Now, if you don't use the L'Hopital's rule, sometimes you can still solve the problem, but you have to do, you have to be good in algebra. Okay, you can get rid of x minus 2. Okay, so how do you do that? So x cubed minus 2 cubed. You have to familiar how to factor this x cubed minus 2 cubed. Okay, that is going to be x minus 2, x squared plus 2x plus 2 cubed. Okay? And I don't think everybody knows that. All right, so then you cancel x minus 2. Right, then you get x squared plus 2x plus 4. Then you apply, then you let x approaches 2. You get 2 squared, no, it's not 2 squared. Here it's 2, it's just 2, okay? So 2 squared, 2 times 2 plus 4, that's going to be 12. The same answer, right? But you have to know this, this formula. Right? You have to know that a cubed minus b cubed is again a minus b, a squared plus ab plus b squared. Okay, otherwise you're not able to use this method to solve the problem. How about the limit as x approaches 0, sine x of x? We know that this is going to be 1, right? But we prove that in a different way. But now use the L'Hopital's rule, it's much easier. So this is a 0 over 0 type, right? It's a 0 over 0 type. Yeah, every time when you write, when you apply L'Hopital's rule, you have to put a note there, remark next to that. So you clear, you know, you are using L'Hopital's rule, and there's the two functions, numerator and denominator, satisfying the assumption. Okay? Then you can use the L'Hopital's rule. It's going to be the derivative of x is 1, derivative cosine x is sine x is cosine. So that's going to be cosine 0, which is 1. Let's try a slightly different problem. So I wanted to try this. Okay, so please do this problem. Clearly, cosine 0 is 1, so this is 0 over 0 type. So you can apply L'Hopital's rule to solve the problem. Right, so it's 0 over 0 type, so you can apply the L'Hopital's rule. It's going to be derivative numerator is 2x. The derivative denominator is going to be 0 minus negative sine x, which is just sine x. So it's 2x over sine x, and then we already find the derivative, x sine x over x. So the reciprocal is the same, right? But you can continue to find, you can continue applying the L'Hopital's rule to this problem, because this is a 0 over 0 type. When you differentiate the numerator is 2, denominator is going to be cosine x. So that will be cosine 0, the answer will be 2. Now, we can generalize the L'Hopital's rule to some other situation. So in the L'Hopital's, in the L'Hopital's rule, A is not necessary to be finite. Okay. So also the limit can be right side limit or the left side limit. Okay. So this is still true. Here's a note. Okay. In this formula, okay, A could be plus minus infinity. Okay, it's not necessary to be finite. Okay, or finite. Okay, the limit can be also could be right side limit or left side limit. Okay, it can be also possible holds for, this is true for, this is a hold for the case when A equals plus minus infinity, or finite, or x approaches A from the left hand side, or x approaches A from the right hand side. Okay, sometimes just one side limit. Okay, as long as it's 0 over 0 type or infinity over infinity type, then you can you apply the L'Hopital's rule. So the value of the function is not necessary to be defined at the A. Okay, so f of like like when A is infinity, of course f is not defined at infinity. Okay, so it's not necessarily, the function is not necessary to be defined at A. Okay. So take a look at the following problems. When x approaches infinity, and here is going to be 2 to the x, okay, and x squared. I think the limit will be infinity. So, but how do we prove it? Because the exponential function grows much faster than polynomial. So quotient should be getting larger, larger, larger. So the answer will be, will be infinity. So how do we prove that, right? So first of all, it is going to be infinity over infinity type. So I can apply the L'Hopital's rule. Okay, I differentiate, and that's going to be 2 to the x, natural log of 2, and 2x. Okay. Right? And you double check again, this still have infinity over infinity type, because when x up goes to infinity, 2x goes to infinity. So you can continue to apply the L'Hopital's rule. So it's going to be x approaches infinity, and that is going to be 2 to the x, natural log of 2 squared, and the 2. Right? Yeah, the derivative of 2x is going to be just 2. Now, this is no longer to be infinite of infinite type. So you have to stop here, don't use the L'Hopital's rule on this function. So just look at this function. The numerator, the denominator is constant. The numerator is getting larger and larger. Of course, it's clearly, it is going to be infinite, right? So that's the answer. Yeah. 2 to the x is a derivative of 2 to the x is going to be 2 to the x times natural log of 2. 4x, why is 4x squared? Why is it 4 from? No, 2 to the x. The x is the power of 2. Okay? And another factor I'm using here is going to be 2 to the x is going to be infinity. Okay? So those are two. This is a constant. This is a constant. And the 2 to the x goes to infinity. Constant times infinity is infinity. Right? So the next one is natural log of x. And here x is to any constant here. And this is a, let's call it a, okay? Here a is a positive number, some positive number. My answer will be 0. The reason is when x approaches infinity, x to any positive power grows faster than the natural log of x. Okay, so the quotient should be getting smaller and smaller. But how do you prove that, right? You apply the L'Hopital's rule. So first of all, you note that x approaches infinity, x to the a is going to be infinity. We also know that x approaches a, natural log of x is going to be infinity. So it is infinite over infinite type. Therefore, you can apply the L'Hopital's rule. Why the second one, the first one, the limit is infinity? Because a is positive. A is a positive number. All right. So now you can apply the L'Hopital's rule is going to be, the derivative of x to the a is a times x to the a minus 1. The derivative of natural log of x is 1 of x. But it's harder to tell x to the a minus 1, right? It depends on the value of a, whether this approaches infinity. So you cannot, before you do that, you cannot say anything, okay? It's not like an infinite over infinite type or 0 over 0 type. The numerator right now, 1 of x approaches 0, but the denominator, maybe not, okay? So we have to modify, simplify this. It's going to be a over, and you move x down, so you get x to the a minus 1 times x. That's going to be x to the a, okay? But clearly, this is going to be 1 over infinite type. It's going to be 0. So that means the natural log of x grows smaller, slower, yeah, grows slower than any power function with a positive power, okay? Because the quotient approaches 0. Okay? We always trying to compare different functions. How do that grow fast? Right? Which one grows much faster? Then you have a sequence, right? So as x approaches infinity, natural log of x grows much smaller than x to the power a. is positive, and smaller than any a to the x is greater than 1. Okay? And this is a comparison. Exponential growth is much faster. So if you deposit a small amount of money in the bank, as long as the interest rate is fixed, by maybe 2%, and the balance grows exponentially. Of course, maybe next few generations, you forgot who has grandson, but they're going to get $1 million. You can easily figure it out. Okay, put $10 in the bank, create an account, and just keep it there. Don't touch it, because you really $10 means probably nothing to you, right? For a long time. Yeah. Then, but the problem is, don't forget the inflation. Okay, so if the inflation rate is 3%, then you're going to get less money, but not zero. Inflation rate is smaller than the growth rate. Interest rate. Yeah, then you get more money in the bank. Okay. I still remember in 1991, when I was assistant professor at University of Michigan in Ann Arbor. I remember I opened a bank account, and I was told that CD, your CD, right? The interest rate is 7.2%. 7.2%. It's great. Yeah, that was it. It never happened. Okay, no. Because I was trying to save some money for my down payment for my house. 7.2%. All right, so let's continue. Find the limit as x approaches 0. Now, speak of interest rate, it's very complicated. Without have a good mathematics, harder to understand. Okay, so you heard about the war between Donald Trump and the bank. They want to increase the interest rate, and Donald Trump said no, don't do that, right? Then why not, right? If they increase the interest rate, ordinary people maybe feel very happy because you can save money, get more interest rate. But the businessman says, nah, I have to pay more back to the bank. Now there's a balance between that, right? If the businessman cannot survive, how can he find a job, right? So it's harder to find the best point. Yeah, this is the point. Someday maybe you own a business, then you want to have a lower interest rate. You don't want to have a high interest rate, right? All right, so this is a x minus sine x is x over. So let's look at that. When x approaches 0, I think all the terms here approach 0. So the difference approaches 0. So this is 0 over 0 type. Okay. So the first thing you have to do is just differentiate numerator and denominator. So this you can apply the L'Hopital's rule. It's going to be 1 minus cosine x, and here's 1 minus the derivative of tan x is going to be secant square x. That's what I remember. Okay, but if we plug, if we plug 0 for x, it's still 0 over 0 type. Okay. Now the question is whether you should continue to differentiate this. I find out you can modify the function first and before you differentiate. It's up to you. Okay, if you you can continue to differentiate numerator and denominator. Right? Then you have to differentiate further and further. So I yeah, you will continue to get the same type of a function, 0 over 0 type. I already see that because the numerator is going to be sine x plus 0 for x is still 0, right? So I don't like the secant x. So it's 1 minus cosine square x. 1, okay? So I'm going to simplify this function. How do you simplify? Well, it is going to be cosine square x minus 1 minus cosine x. Then here's cosine square x. Okay. I know that I know the limit of cosine square x is going to be 1. So how about 1 minus cosine x? That was a negative sign. So you can put cosine x minus 1, cosine x plus 1, 1 minus cosine x, and cosine square x. And clearly you can cancel the trouble term 1 minus x. Right? So you will get negative sign, negative cosine x plus 1, and then you have a cosine square there. So now you just plug 0 for x. It's negative 1. 1 plus 1 is negative 1/2. Okay, I did not apply the product. I did not apply the L'Hopital's rule to that function. Instead, I just simplify and I get rid of the term 1 minus cosine x. Okay, if you continue, you have to differentiate secant x and just getting more and more complicated. Oh, we can try, you know. So we can, if we are given this, if you are given this, right? And you look at this is a 0 over 0 type, right? And how do you do that next step? So you, okay, I'm going to differentiate. Okay, fine. So I get sine x. And here the derivative 1 is gone. So it's negative 2 secant x. Now what is the derivative of secant x? Huh? Secant tangent, right? Secant x, tangent x. Not too bad. All right, so you're not able to simplify. Then you have trouble. Oh, too many terms, right? And the secant square x, you can differentiate. It's possible. Yeah, secant. Okay, so it still will be 0 over 0 type. But I think we should simplify stuff. I cannot, don't be so stupid, you know, continue. Where's my, okay. I'm going to find my, you cover my pen. Okay. Yeah. Why you can simplify? Because sine tangent x is almost like you know, tangent x is going to be sine over cosine. So you can get rid of sine x. Okay. So you get 1 and put the cosine x on the top and the negative 2 secant square x. That's okay. So when you plug 0 for x, secant x is going to be 1. So it's just 1/2. Okay. Yes, secant x is 1 over cosine x. Cosine 0 is going to 1. So it's negative 1/2. So you have to stop here. Otherwise, it's just more complicated with differential. Yeah. So here's the next one. I think this is clearly the derivative. This is going to be 0. The reason is this is 0 over this is infinite over infinite type. So you can use a L'Hopital's rule, but I'm not going to differentiate immediately, because when I see natural log of square x, I can take 1/2 out. Then natural log of x over a polynomial, the limit is always equal 0. It's obvious, okay? We already know that. But you can also differentiate, right? You suppose if you don't know this, then you have to differentiate this to 1/x and 3x squared, and you get, after simplifying, you got 6x cubed, and clearly this is going to be 0. Okay? Now there are some functions does not look like a quotient at the very beginning. Like here's x, sine pi of x. Right? Now this is a product of two functions. Right? I cannot say it's 0 over 0 type. How can I make a change? Right? I can change it to sine pi over x over 1/x. How about this? And this is going to be 0 over 0 type. Okay? I have to use you can use substitution. Let u to be 1/x. And when x approaches 0, when x approaches infinity, u approaches 0 from positive side. Okay? It will be sine pi times u and over u. Okay? So this is going to be 0 over 0 type. Then you can apply the L'Hopital's rule. It's going to be 1 and the cosine pi u and times pi. Right? So the limit is going to be pi because it's goes in cosine 0 over 1 pi, it's going to be pi. All right. There's similar argument for the next problem. E to the negative x squared. Okay, this is still product, right? Product. So first, you have to express as a quotient. Oh, that's natural. E to the x squared, right? So this is going to be infinite over infinite type. Right? So you can apply the L'Hopital's rule to find. Now the problem here is if you use a substitution, it's better, but right now let's do it. Okay, so differentiate once, you will get 3x squared, and here's e to the x squared and 2x. That's a problem, but you can cancel it. X squared over x, cancel it. So you got 2e to the x squared and 3x after you simplify. Then you look at this again. Okay, this is still 0 over 0 type, infinite over infinite type. So you can apply the L'Hopital's rule again. Okay, so it's going to be 3, just 3, and here's 2 e to the x squared and times 2x. And clearly, this is going to be 0. Why? Because x times e to the x squared approaches infinity, and that's the denominator, right? In the denominator. So that's why the quotient approaches 0. Okay, then. So in order to apply the L'Hopital's rule, you have to express a function as a quotient of two functions. Now, what happens if you don't get such things, right? Like a product, but you have to convert it to a quotient. And how about the difference, right? For example, problem number 52 and 54, and I just randomly pick up a one. So when x approaches 0 from positive side, 1 of x minus arctangent x. Okay. Arctangent x, we just learned the derivative, right? The inverse function of a sine. It's going to be 1 over 1 plus x squared, the derivative. Okay. This is not quotient of anything, right? It's a infinity minus the infinity type. I cannot apply L'Hopital's rule directly. Okay. So the only way I can do is I'm going to combine them. I get arctangent x minus x. Then this is a quotient, right? So it's a 0 over 0 type. All right, 0 over 0 type. All right, we have to know that what is the derivative of arctangent x, which is given. Okay, it's 1 over 1 plus x squared. So you can apply the L'Hopital's rule to the problem, or it's probably complicated, right? The derivative of the denominator is going to be arctangent x plus x times the derivative of arctangent x, which is 1 over 1 plus x squared. All right? Just be patient, yeah. So here's 1 over 1 plus x squared and minus 1. I think, yeah, you have to simplify the numerator denominator first. So after you simplify, you will get the numerator is 1 minus 1 over, you see, the numerator is negative x squared 1 plus 1 x squared. The denominator, we have to combine them. You get also 1 plus x squared arctangent x plus x. So after you simplified, get rid of 1 plus x squared, you will get something like this. Okay. Well, this is still a problem. Does not get simpler, but it's still going to be this 0 over 0 type if you plug 0 for x. Okay, but I already know the limit is going to be 0. Why? My feeling is that the numerator is x squared. The denominator is about x. Okay, because arctangent x is about x when x is small. Okay, arctangent x is about x. Okay, so then you have another x. So I'm pretty sure this is going to be 0, the limit. Let's see. I'm going to differentiate the numerator denominator again. Okay, so don't worry about it. It's a little bit complicated. It's 2x arctangent x plus 1 plus x squared, and the derivative of arctangent x is 1 over 1 x squared and plus 1. I think it's great. It's cancelled, and this is not going to be 0 over 0 type. The numerator approaches 0, but denominator approaches 2. Why is 2? Because that's 1 plus 1 is 2. The first term is 0. So it approaches negative 2 times 0 and 0 plus 2. Okay? So the answer is going to be 0. right? So this is, then how about this? Then you say, okay, I really cannot even combine them, right? There's no way you can combine them. How do you find it? No, you cannot differentiate because only you can apply L'Hopital's law only to the quotient function, limit of quotient function, right? And that's what we did. You know, we combine them. It's a difference and put them together, and then I get a 0/0 type, and then I can find the derivative, right? But now x minus natural log x, that's so simple, two functions, you cannot combine them. Apple is apple, orange is orange, how can you put them together, right? No. Well, mathematics, you know, this just, I think it's like any other subject in natural science. So you have you face a challenging problem, you have to find a way to solve it. That's it. Right? Any kind of problems. Then some are you maybe find a better way to do that. Some, you know, maybe you find a longer way to fix the problem. Right? Right. So, but I remember, right? Natural log of x grows much smaller than any power function, and also grows much smaller than this. Okay, so I guess the first term grows much faster than the second term. So the gap between those two is getting larger and larger, right? Okay. So the difference is getting larger and larger. So I guess the difference approaches infinity. Right? That's my, you know, you have to get another something, right? All right, so I'm going to modify. I take x out. How about this? All right, that's product becomes. That's called algebraic skill, okay? So it becomes a product, and you will see that what is the limit of this part? The limit of this part is 1 minus 0, right? It's 1, because the second part limit is 0. We already know that, remember. The first part, it approaches the infinity. So you have two terms, the product two terms. The first term approaches the infinity. The second term approaches 1. The product approaches infinity. It's obvious, clear. Okay, so that's why it approaches infinity. Then, I didn't use L'Hopital's law. I cannot use L'Hopital's law here. Okay, it's not a good idea to use L'Hopital's law. You cannot use L'Hopital's law. Okay, yeah. But I'm modifying the function so I can see the limit. I can convince, you know, other people this is my correct answer, you know, right? If you get larger number and multiply by another number, maybe smaller than 1, but it's getting closer to 1, I think the product is getting larger. Like, you know, one side like a 1 million, 1 trillion, right? Other side maybe 0.5. That's okay. 0.5 times 1 trillion is still a huge number. Okay. Yeah, those numbers again. Yeah. The whole big of the universe. Nobody knows, right? I think it's huge. I have rough estimate, but our universe is only one tiny dust in the space, and the Earth is much smaller. It's invisible. Okay, it's amazing. Yeah, I was looking. Yeah, you can type universe size and go YouTube, and you see the comparisons, and you find out you're so tiny, and suddenly by the end they say, oh, this tiny Earth, right? Space is only like one small point. There's so many people there, and including you, and sometimes you're happy and happy, you have love and no love. So yeah, if you think about this way, it's why we're here, why we come here, Okay. Okay, now let's look at another strange problem. We have to solve it, right? So this is going to be the limit as x approaches infinity, x to the, it's not going to be infinity, but x goes to infinity, but when x goes to 0, so this looks like infinity to the power 0, okay, type. I cannot apply L'Hopital's rule directly to this problem. Let's find a way to solve it, okay? But I remember the limit as x approaches infinity, this is going to be 0, right? Okay, this is going to be 0. All right. So this is going to be, I have to modify, right? So the way to do is put the e natural log. Yeah. Then if e to the, you move 1 of x to the side, it's 1 of x, natural of x. Then you just need to look at this limit, right? But this limit I already told you it's 0. So it's going to be e to 0, which is 1. Yeah, it's interesting. X to the 1 of x approaches 1. You can have a 1 million to the 1 of 1 million. It's almost equal 1. Okay? It's not like a very big number. It's getting smaller and smaller. Okay. Okay, so the limit as x approaches infinity, x to the e to the negative x. So this is again, it's the infinity over 0 type problem, right? Why? Because e to the negative x is going to be e to the negative x. It approaches 0. Okay, so but x approaches infinity. So this is kind of like an infinity to 0 type still. Okay, how do you solve this problem? Okay, so this is going to be e to the natural of x, e to the negative x. Okay. Right, it's the same trick. And that is going to be, it's, hold on, I wrote down a mistake. So the x is under this, okay? So then that is going to be e to the negative x, natural of x. And let's rewrite this. It's going to be natural e to the natural x over e to the x. So in order to find the limit of this, you have to find the limit of the power function. I think the limit of power function must be 0. The reason is natural log of x divided by x, the limit is already 0. and divide by e to the x, the limit must be 0. Okay, so limit as x approaches infinity, natural log x of e to the x. This is going to be 0 over 0 type, infinity over infinity type. So you just differentiate and e to the x. And clearly this is going to be 0. Right? It's going to be 0. Okay, so you put it here. And you solve the problem. I hope you find the time to do all kinds of this kind of exercise. If I put this problem on the test, I don't want to see, I have no clue what's going on. I never see the problem like that because we did so many problems in the class. Okay, so when you prepare for the exam, you have to look at the notes. Okay, all those problems in my brain. So when I make an exam, when I make this exam, this problem pumps up automatically. So I just type. Okay, so you should go through those problems if you have time. When I was in undergraduate student, I know I'm not smart than other kids, students. Now there are no more kids in college. I don't call them kids, because my class had 43 students. 7 students did not even pass the exams to get into school because that was the #1 math competition in the state. So they just pick it up by the university, come to our, and I was, I took all the tests. That's why I did not think I'm smart. I did all the exercise. Besides that, I did all the remaining problems in the section. Okay? And at the very beginning, the first semester, I still remember my total score is below at the bottom, and I took time. Slowly, at the end, after 4 years, the professors have to select 1 student from each class to give a silver medal. I got a silver medal. Okay, but my average score, my total score is still not the top because of the very first semester, I did not do well. Right? But I make progress. My slope is positive. Yeah, that's it. So when you think you're not smart, then you can study well because you have to spend more time on the subject. Okay, that's what they did in college. Okay, let's do one more problem. My high school classmates, I still remember how their other 2 students are very good in math, but one of them became a mathematician. He's a professor at Cambridge University. From my high school, yeah, a surprise. Another student, those are 2 good students in mathematics. I'm not, okay, I'm not. He got a PhD in statistics. He was working for JP Morgan, the Chase Bank, yeah, New York City. All right, let's do this next problem. Okay, let's do one more problem, then we're done with this. Wait, we probably did all the problems here. Okay, let me check. Oh, I found one. It's a nice problem. Number 46. All right, take a look at this. Okay. All right, so this is whoa, what's going on here? Okay. It's not a quotient of 2 functions. Okay, but let's look at the natural log, right? Inside, what is it going on here? So 1 minus 1 of x approaches 1, right? Because 1 of x approaches 0. 1 of x approaches 0 as x approaches negative infinity. So this approaches 1. So natural log of 1 of this approaches 0, right? Because natural log of 1 is 0. So this is going to be like an infinite type, 0 type. Yeah, we can modify it to we can modify, right? To use a L'Hopital's rule. What I'm going to do is I'm going to modify in the following. Okay. Then once I express in this form, I have to use a substitution. Okay, let u to be 1 of x. So it's natural log of 1 minus u over u. Now, since x approaches negative infinity, so 1 of x approaches 0 from negative side. Okay, from negative side. Maybe not necessarily to know that, but at least for this limit, I have to put a 0 to 0 negative. Okay, now this is going to be 0 over 0 type. It's in the quotient form. So you can apply the L'Hopital's rule to solve this problem. Okay, so it's going to be, it's a 1, and the derivative of that is going to 1 over 1 minus u times negative 1. Okay, but why is negative 1? Because the derivative of 1 minus u is going to be negative 1. Okay. Okay, now this is no longer in the form you can apply L'Hopital's rule here, because this is going to be a constant over 0, over 1. You know, so it's just negative 1. Yeah, plug 0 for you, let's get a negative. So the answer is negative 1. Okay. Right, I believe 51 is a homework problem. Can you work out this problem in the class? Right, so you cannot easily get the limit. Just look at that. We have to modify this, right? So x over 1 over minus x, the first one, it approaches 0. Approaches infinity, right? Infinity over infinite type. Okay? So infinity minus infinity, so it cannot determine the limit at the very beginning. So you have to modify this function. Okay? You have to express it as quotient of 2 functions, then apply the L'Hopital's rule. Right, combine them into one fraction. Then I believe that it is going to be 0 over 0 type. Yeah, it's 0 over 0 type. Yeah, natural log of 1 is 0, and x minus 1 becomes 0. Okay. I probably have to differentiate twice. That's a possibility. So we can, the numerator is also 0. Yeah. So it is going to be, let's find the derivative. The denominator is going to be natural log of x plus x minus 1 divided by x. Okay. This will be natural log of x plus x times 1 of x minus 1. Okay. Be careful when you differentiate. So if you make mistakes, you're not going to get the right answer. Right. So I get the numerator, I just get a natural of x. The numerator just make it a natural of x. The denominator is going to be natural of x plus x minus 1 of x. I think this is still 0 over 0 type. Okay, but I don't like the x in the denominator, so I have to modify. I multiply the denominator numerator by x. So get natural x, here's x, natural x plus x minus 1. Okay, this is 0 over 0 type when x equals 1 and the numerator is 0, denominator is 0. So we continue to differentiate. So I differentiate the denominator, numerator is going to be natural x plus x times 1 of x. And here we get same and the plus 1. I think this time the limit is going to be 0 plus 1, 0 plus 1 plus 1 is going to be 1. Okay, so that's the answer.